Hello. In the previous video, I introduced the idea of using the length as a probability, assuming that probability is proportional to the length. But in the second example, I also said the length example is not general enough. It may not work in some examples. So we are going to generalize the length to the next level. This is a simple idea. So in mathematics, you can like in our sense, we can imagine up to 3 dimensions. The space we live in is a three-dimensional space. So then let's think about 0 dimension, 1 dimension, 2 dimension, 3 dimensions. 0 dimension is a point. One point is a 0 dimension. So there is no measure for this. It just exists. There is no big or small. A point is not a thing to measure. When you collect an infinite number of points, continuously infinite number of points, then it makes a line, right? And then it becomes one dimension. So it's one dimensional. There is one direction, so it's one dimension. And it is a line. A line is an object in one dimensional space. And it's only in one dimension, so when you measure how big a line is, it is a length or width, height, does not matter. A line is a one-dimensional object. We used one-dimensional object to handle the probability, but it was not general enough. So we are going to extend our dimension to 2. When you collect infinite number of lines, say line, 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 when you collect them, infinite number, continuously collect them, then it will make a square, like a paper, a flat square. It will be made, or square is composed of infinite number of uncountably many continuous lines. A square is a two-dimensional object. So on two-dimensional plane, you can draw a square. And when you measure how big a square is in two dimension, the measure you are going to use is its area. Area for a square is easy to calculate. It's simply multiplication of width and height, right? You know how to calculate the area of a rectangle or a square rectangle. And if you want to extend to the next level, square, 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 then when you accumulate them, it will become a three-dimensional cube. Cube, you know how it looks like. And cube is like the object in 3 dimensions, and it has 3 dimensions, so its measure is a volume. Volume is multiplication of width, height, and depth. So that's a very simple idea. Anyhow, what I want to say here is we used to use a line to explain the probability, to motivate probability. And also I said a point within a line has no measure, no length, right? A point is a zero-dimensional object. So when you choose one point on a line, its length is 0, right? But the problem was length was not enough. One dimension was not enough, not general enough. So we are going to consider 2 dimensions from now on. So if you think about a square or a rectangle or any shape on 2 dimension, you can calculate its area. Area is its measure, and also still one point has no measure. Still the idea that the result that one point has no probability still holds in 2 dimensions, but it is more general than the one-dimensional analysis. Then of course it will be more complicated. When you consider the length, what you need is just one-dimensional line. But now we are going to use two-dimensional graphs. So the horizontal axis is ounces, the amount in a tall size coffee. So 11.8 ounce, 11.9 ounce, 12 ounce, 12.2 ounce, 12.3 ounce. And the vertical axis has something like probability. It's not exactly probability, but they are going to be used to calculate the probability. So what is this? You can think it as a curve of this uh, this shape. It's like skyline, like many buildings next to each other. And what we are going to do here is we are going to interpret. So when you have one dimension, we only consider this length, but now we will consider area on the interval below the curve. So previously, when you calculate the probability between 11.9 and 12, we only considered the length of that interval. But now, not only the length, but also we have to consider its height, right? So you are interested in this interval, then you have to calculate its area on the interval below the curve. So this is how we do. Probability between 11.9 and 12 is the area of the shaded, the colored blue area. And the blue area is a rectangle, so easy to calculate. The width is 0.1 and the height is 2.5. Remember, you have to use these numbers when you calculate the height. So its height is 0.5, it's 2.5, it's 3, it's 1. So the answer is 25%. 25% lies within 11.9 and 12. Similarly, you may calculate the interval on anywhere. So probability between 12 and 12.1 is another rectangle, and width is the same, but height is different. So on this area, the curve is higher than here. So you multiply 3 different height. So then it's 30%, right? The area is the probability. So 30% is the same. So then, as you see, the difference here is this interval and this interval has the same width, but the resulting probabilities are different. So the probabilities are not proportional to the length, but there is another dimension, which is the height. So if the height of the curve is different, then the same interval may have like the intervals with the same length may have different probabilities. So it's more general. And that's the idea. And even if the shape is not a rectangle, still it's not a problem. In this case, it's just elementary school math. Like, what is the probability on this interval? On what is the area? What is the area of this colored blue shape? Then you may just break it down into two rectangles and sum these two areas. It's exactly how you calculate the area for this shape. Just split them into two rectangles, and you know how to calculate the rectangle area of the rectangle. So the probability here is 55%, and this curve captures the CDF that we had in our previous example. The coffee example has this interpretation. This is a new and interesting interpretation, and we say the curve is a probability density function. So this is a graph. So it is a function. When you for each value there is an output. So it is a function, and this function is called probability density function. So these numbers 0.5, 2.5, 3, these numbers are probability densities, not exactly probability. Oh, by the way, I forgot to say this. Still, the 1 point has no measure, has no area. If you choose 1 point, The width is 0. Even if there is a height, width is 0. So the area is 0. 0 times anything is 0. So one point has no probability. That is still true. Anyhow, the curve is called a probability density function, usually abbreviated into PDF, and usually denoted as lowercase f. CDF was denoted as uppercase f, but now PDF is denoted as lowercase f. And it is used to calculate the area below the curve. And of course, it should be always positive or 0, but what's tricky here is it can exceed 1. It is not exactly probability. That's the major difference. Um, Anyhow, we are so PDF is in this example. This is just a simple example that allows you to calculate the area using rectangles. But of course, in practice, probability density is more smooth, and different distributions have different probability density. So I'm giving you 4 examples. It is a uniform distribution. Uniform distribution has a rectangle shape, which is good. So here it shows that 0, 1, 2, 3, 4, 5, and then there is some probability between 1 and 4, but there is no other probability between 0, 1, and 4 and 5. And so it is uniform distribution because it is uniform, flat. And exponential distribution has a decreasing probability, starts from 0, and 0 is the peak, and then it smoothly decreases, exponentially decreases. So we call this exponential distribution. And gamma distribution has another smooth shape, but has a peak here. From 0 it increases and then decreases. So this is a gamma distribution. And normal distribution has another smooth density function, but it is centered around 0 and has bell-shaped. So different probability distributions have different probability density. Still, the idea is the same. If you are looking for probability between probability between 0, 1 and 2, oh, I painted on the other side. Anyhow, so then you have to calculate this area. For the uniform distribution, calculating this area is not a big deal, right? It's a rectangle, but exponential distribution is a little bit, it's not flat, it's not a straight line, and gamma distribution looks even more difficult to calculate, and normal distribution also weird shape. So in general, you cannot calculate the area directly using like this much like rectangles. So what we need is integration here. Integration is how we calculate the area below a function. If you no, calculus course is a prerequisite for this course, so I believe you know what is an integration, and at least you may remember the sentence that integration is calculating area. So when you have a density function, lowercase f, then the area between 1 and 2 is an integration of f density between 1 and 2. And probability between 3 and 4 is an integration of the density between 3 and 4. So this is the relationship between density and probability. You don't need to integrate at all in this course. I'm telling you it's an integration, but you do not need to calculate any integration from now on. So don't worry even if you forget how to integrate a function. That's not a problem. But it's an important concept. Okay, then intermediate summary. So far, we have studied the difference between a continuous random variable from a discrete random variable. So simply speaking, continuous random variables have uncountably many outcomes. It causes a problem. And second, it has zero probability at a single point. So these two properties are troublesome. So causes problems. So we need to consider alternative approaches to define probability. And I introduced two major methods to define the probability. One is cumulative distribution function, which is defined as probability smaller than something, right? Uh, and the other method is the probability density function approach. When you have probability density, then you can use integration to calculate the probability. Any probability can be calculated using the integrations. Okay, so in the next video, I'm going to start the normal distribution. I have not considered normal distribution so far at all. So far, it was just the general properties about continuous random variables. So see you in the next video. Uh, And in the next video, I'm going to use Microsoft Excel to calculate CDF of a normal distribution. So I want you to prepare, like open Excel and watch optional videos about Excel before watching the next video. Thank you.